So we are going to take a look at lesson 1C. We're looking at 2.3, which is all about sketching polynomials. So some background, some background knowledge that we have from our Desmos activities, because there were two Desmos activities. One Desmos activity was about end behavior, and the end behaviors split into the 4 sections. That it was even degree or odd degree, positive or negative, and even was up, up, even positive is up, up, even negative is down, down, odd positive is down and then up and then down. And then I did the snazzy trick where I took those two odd ones and made a straight line to show you, yeah, if it has a positive slope, it starts in the negatives and heads up into the positives. So that was one of our Desmos. The other Desmos was creating those polynomials to go through certain roots. And you might have had one that we wanted to go through like here and here. And let's say that was -1 and that was like +4. And what you did was write the polynomial x minus 4, x plus 1, x minus 4. And it looks like that. And we were looking at that kind of thing and tying this factored form and our graph together. Okay. There was something snazzy that happened about one of them, and it was a graph that kind of looked, and I'm probably mistaken in the numbers, but something like this. That it started like that, and then it kind of went like that, where it only hit it once. That was a really tricky part of the Desmos, and that's going to come up today in our lesson. Okay, but this was our background information, just as we're what we know already. So this is what we know. We've tied these two together with Desmos, and we're going to be building to this. Oops, and then I'm going to hit a button and erase it. We're going to build to this kind of shape. Okay, so all this ties together. All right, so we are on page, and I'm going to pretend like I know, but I don't, 19. So this is page 19. Now, I'm going to look at this polynomial. Now, I don't want to multiply it out because I don't want to. Okay, so if I did multiply it, though, I would have x times x times x, and there's a positive 1 here. And that multiplied all out would give me a positive 1x cubed. And then there'd be a bunch of other numbers, and probably a big number at that end. But I don't want to multiply it out. Do I have the ability to? Yes, I do. But I don't want to, so I'm not going to. I'm not going to create more work for myself than I have to. All I need to know is what that leading term would be in order to determine the end behavior. That's why I have to do this. So being a positive and an odd degree, that tells me that my end behavior, I'm going to abbreviate EB. Positive and odd is going to be either you can write it down up in words or you can write it in arrows. Now, my zeros are going to be based off of these factors. So you see how I have this factor, and this factor. Small yellow, and it really wasn't distinguishable. So I'm going to set this all equal to 0. And the only way to multiply to 0 by the zero product property is that something has to be 0. So I get x plus 2 is equal to 0, which gives me x 2. Then I get x minus 6 is equal to 0, which gives me x 6. And last but not least, x plus 8 is 0, so x is negative. So I have 3 zeros. -2, positive 6, and -8. So I found my end behavior, and I found my zeros. There's one other thing I could find, and that's my y-intercept. This is nice to have, but not required. So required, bonus. Okay. So when I find my y-intercept, we make the x 0. So we would say y y equals 0 plus 2, 0 minus 6, and 0 plus 8. Now, depending on the numbers, you might be able to calculate this, you might not. 2, negative 6, positive 8. To me, the most important thing here is that this will result in a negative. The negative that it does result in is 96. So negative 96. Yikes. So good thing I'm not graphing this precisely. However, I'm creating a sketch. So now I'm going to take these three pieces of information that I have. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So these three zeros, negative 2, positive 6, and negative 8, all correspond there. Now, the fact that my end behavior here is down up, that's going to go, this side's going to go down forever. This side's going to go up forever. Okay, there's my down up and there's my zeros. Now, I do know negative 96. I'm just going to place it here towards the bottom and write a negative 96 on it. Should also probably label these. So I'm going to go through here. That. Now, this is a sketch. You'll notice that when I created it, I did not make sure that that hill was perfect. I did not find out how high that hill was. I did not find out how low that valley was. We would need our calculator to do that, and I'm doing all of this sketching without a calculator. And that's why we're calling this a sketch and not a graph. Okay, it's just giving us the general shape of what this polynomial looks like without any of the precision that a graph would have. Okay, and that's my sketch of that cubic polynomial. Now let's take a look at the one next to it. All right, so I've got, for zeros, I'm going in a different order this time. That's fine, as long as I find them all. Zeros, I have x minus 2 is equal to 0, which gives me x equals 2. X plus 1 equals 0, which gives me x is negative 1. And x minus 7 is equal to 0, which gives me x equals 7. So 1, 2, 3 zeros this time. Now, when I go to find my end behavior, x, 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 and there's a negative there. That's important. So I have a negative 1 times x times x times x, which gives me negative x cubed. Ah, negative x cubed. That is going to have an end behavior of up, down, or up, down. Okay, now I can find my y-intercept. Again, my y-intercept is bonus. We don't really need it, but it's nice to have sometimes. Oh, this one's easier to calculate too. Even better. Positive 2 times 1, which is a negative 14. Okay. My x-intercepts, 1, 2, 3, 4, 5, 6, 7, negative 1, and we're going to throw negative 14 down here again. Okay. Boom, boom, boom. I'm going through all of those points. Okay. And now I know my ends. That end is up. That end is down. I'm going to kind of go like that. And again, I did not find out how high this hill was. Okay, similarly, I did not find out how low this valley was. That's okay. That's a problem for a different day. Okay, so now I want you to pause the video and try this problem. Be careful though, because I have 1, 2, 3, 4. Okay, so pause the video and try it, please. Did you try it? All right, so here's what I would do. I have 4x equals 0, x minus 10 is equal to 0, x minus 5 is equal to 0, and x plus 5 is equal to 0. That's going to give me x equals 0, x equals 10, x equals 5, and x equals negative 5. So this time I have 4 zeros. 5, 10, negative 5. Yeah, I know I didn't label all the other ones. Since 0 is one of my zeros, it's doing double duty as the y-intercept. So, okay. So now, my end behavior. We have 4x times x times x times x. They give me 4x to the 4th, even degree and positive. So my end behavior is up, up. Means this side goes up, this side goes up, and then in between I'm going to kind of make a W-ish. We're winning. Okay. As a reminder, I said it on all the other ones. I did not find out how low those valleys are. I did not find out how high that hill was. If I was looking to graph this, I would need to find that information. And the only way with your current skill level in pre-calc is to use a graphing utility, whether it's Desmos or a graphing calculator for that. Okay. So, multiplicities. This is a really important thing. So if I have something quantity squared, we call that a multiplicity of 2, and it's also sometimes called a double root. Okay? So what would happen to the graph is it created that bounce. Do you remember in Desmos how you had that one where it didn't cross, and this kind of looked like a parabola-ish? Well, that was because it was an even multiplicity, or it had this double root. Okay? So when a polynomial has a multiplicity of 2, I'm going to add for any even multiplicity. The graph is always, ready for this fancy word? Tangent to the x-axis at x equals a in the graph. And that means it bounces on the axis instead of going through it. So you can see how here it had been in the positives and it stayed in the positives instead of being in the positives and then heading into the negatives. That's what we're referring to when we say tangent to the x-axis. So you can see right here, this example here has a tangent to the x-axis. Whereas this one is going through. Make sense? So this being tangent also will tell me that it has an even root. So it could be a double root or a quadruple root. And so that tells me in the factored form, we're going to have something that's going to have x plus 3 squared. That's squared because of the even root. Okay. Where we have even roots on this one, we have an even root here, where it's tangent, and at 3 as well. But then at 1, we have an odd root because it's going through. Now, if you decide to study further, you'll be able to tell the difference between a double root and a quadruple root because they look slightly different. They flatten out more at those roots. But for the purpose of what we're doing, I'll give you the degree so you'll be able to tell what it is. Okay? So when we take a look at this one, when we write our zeros here, x squared is equal to 0, that's going to give me x equals 0 with a multiplicity of 2. So we want to make sure we indicate those multiplicities. X minus 2 quantity squared equals 0. Well, that's going to be x equals 2 with a multiplicity of 2. And so again, that even multiplicity is going to tell me that we're bouncing at those values. And then x minus 1, and that's just going to be x equals 1. When it's a single multiplicity or with that power of 1, we don't put a label on it. So, Now this one, when we do have to take those powers into account when we talk about what the degree is. So when we do that in behavior, we have x squared times an x squared times x. So it would be x to the fifth. That's going to be a down and up. Positive x to the fifth. 0 being an x-intercept means that it's not going. I have my y-intercept as well. 2. All right. So what we're going to have, we have down and up. Now at 0, we're going to bounce. So we want to see bounce on that, goes through the 1 and bounces there. All right. So these are a little different because they're not factored. But it does make it easier to find the end behavior to start. So on this first one, I'm going to do end behavior first. We have an odd degree, and it's positive. Oops, sorry. So we know that means it's going to be down and then up. And now I'm going to take it over to the side and set it equal to 0 so that I can factor and find those. We've done this skill before. So all I'm doing is taking a skill that you already know and combining it. Start by pulling out an x out of the whole thing. And then I want to think about what multiplies to 10 and adds to 7. I don't have a leading coefficient to worry about. That's how I can do that. And so I get x plus 2 and x plus 5. So my zeros here are 0, negative 2, and negative 5. No multiplicities on any of these. And the reason I know that there's no multiplicities is because my exponents are all to the first. That means I'm going to go through all of my axes. So there's 0, negative 2, negative 3, 4, and negative 5. And my end behavior was down, up. So we're going to go down. So it's going to go up. Now I know that I have to go through all of these points and not bounce at all. Again, I'm not finding out how high that hill is. I'm not finding out how low that valley is. That question is going to be answered eventually. Okay, that's just not the objective of today. Today is creating these general sketches of the graph. We're not making them precise graphs. Ooh, this one's a little interesting. It involves a different strategy of factoring. I wonder if you remember it. So to start, we're going to say our end behavior. We have a positive cubic, which we know is a down, up. So now I need to do my factoring. Yeah, x cubed, I probably could have fit it over there, but I write kind of big, so I kind of moved it to the side. That way I don't run out of space. So, coffee. All right, so x cubed plus 2x squared minus x minus 2. So since I have 4 terms, you see I have 4 terms here, 1, 2, 3, 4, polynomial, and there happens to be a nice pattern in these terms. So this doesn't work with every 4-term polynomial, but it does here in this one. We're going to look at 2 terms at a time, and we're going to use a strategy called grouping. So when I look at just these first 2 terms that I have highlighted in yellow, I can factor out an x squared out of both of those. See how? And that leaves me x squared, x plus 2. Now when I look at these 2 terms over here that I have highlighted in blue, I can factor out something. And it's not much, but I can factor out a negative 1. And I'm left with, wait for it, x plus 2. Now that fact that they matched is what's really critical. That's why I can continue doing this. Okay? See those 2 pairs matching with my x plus 2? Well, because I have x squared of those x plus 2's and a negative 1 of those x plus 2's, I can say I have x squared minus 1 of those x plus 2's. So snazzy, right? Now notice, my exponent here is still a 1. It is not a square. Yes, I know I had 2 of them, but they were not 2 that were multiplying against each other. Okay? And if I took this and distributed it, I'd have x squared times that and a negative 1 times that. Okay? Which is exactly what I had in the set before. So I can factor the x squared minus 1 again, or I might set it equal to 0 and solve by taking square roots. That's perfectly valid as well. Okay, 2 different ways of getting to the same thing. And so my zeros here are plus or minus 1. I'm writing it like that because I don't want to write it twice. Let me tell you, mathematicians are lazy. And a negative 2. Then behavior. I also can find my y-intercept on this one because it's not 0 this time. Hey, it's not 0. Okay, bonus. Because remember, we can find the y-intercept, but we don't really need it. 0, 0, 0, minus 0. Well, minus it instead of plus it. Big difference there. I was being sarcastic in case you couldn't tell. Okay, and a y-intercept of negative 2. Again, that y-intercept is just, it's fluff, it's bonus. But I like it. 1, negative 1, negative 2. 1, negative 1, 2. These all will go through on all of them because I don't have any multiplicities. Oh, negative 2. Don't forget about that one. Look at that. How cool. And my end behavior was a down, up. So down, up, and then you're going to see a hill and a valley. And I don't know how tall that hill is, and I don't know how low that valley is, which you should be able to tell me because I've said it a bunch today. All right. So following graph shows an 8th degree polynomial. Remember, we only have fancy names up to 5. Past that, we just usually call them blank degree. List the polynomial zeros with their multiplicities. All right. So this is an odd multiplicity. This is definitely an even one. This is an odd. This is an odd. That's an even, and that's an odd. Okay. And I knew because these two in green have to be even because they don't cross the x-axis. It was in the negatives and stayed in the negatives on both of them, actually. You can see how it was negative, 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 still in the negatives. Negative, 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 still in the negatives. So those two that I have highlighted in green have to be even multiplicities because of those balances. Okay? So my odd multiplicities, I've got 1, 2, 3, 4 of them. 5, 6, 7, 8. So that accounts for all of them. So my zeros are negative 15, negative 10 with a multiplicity of 2. I'm just writing M2 for that. Negative 5, 0, 10 with another multiplicity of 2, and 15. And you can see, if I tally these up, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 zeros right there for my 8th degree polynomial. Right, so now we're going to write some equations from the graph. Not very different from what we were doing. Same ideas, just going the other direction. And sometimes we're going to write our equation in factored form, and sometimes we're going to write the equation in standard form. So, I'm going to first identify our zeros. And I have a scale on the x-axis. You notice that. So if you actually look, these two graphs are different. This one on the left, notice there's no label on the y-axis. Whereas this one on the right does have a label. This is a really critical difference because if you notice, all my sketches, I did not really label my y-axis. Sometimes I marked where a y-intercept would be, but I didn't label it. Okay? So, this one on the left is actually going to have a lot of different answers. And the one on the right is only going to have one answer. All right, so the one on the left, let's start with this one. I can see that I'm crossing at negative 2. I'm crossing positive 1, and positive 2. Okay? Now, and what I'm going to do from there is say y equals, I'm going to write an a. This a could be literally anything. That's why I'm using a. A for anything. X plus 2, x minus 1, x minus 2. Now, in the directions, it didn't say it had to be in standard form or factored form, so I'm going to leave it in factored form. If it had said standard form, then I would have multiplied them all out. That a could be anything in this problem as long as it was positive, so anything greater than 0. The reason we wouldn't want it to be negative, well, 0 would be no function at all. But negative would have n behavior that was up down instead of the down up. Okay, so a can be any positive number. Okay, anything greater than 0. Now this one here, you can see I'm crossing at -2, -1, and +1. All of those have going through, so they're odd multiplicities. Okay, plus 2, plus 1, x minus 1. But this problem is a little different. I'm still going to write y equals a times it. But you notice here, I have this, and I know I'm crossing at 1 for that y intercept. See that? Crossing at 1. And here, yeah, I crossed at 4, but was it 4 or was it 8? Or I don't know what the scale was. Maybe it was 400 for all I know. Yeah, exactly. That's why the one on the left has infinitely many answers with having that constant a where a could be anything. And this one's going to only have one answer because I have that scale on the y-axis. Now, there were other values you could have pulled, but for me, some of the other ones, I don't know. I'm looking at it, I'm like, at 2, is that -5? Or is that -6? I don't really know. So to me, I see that the 0, 1 looks like the clearest point that I can tell. So I'm going to go through the point 0, 1. So what I'm going to do, because my points are labeled x, y, so say 1 a times 0 plus 2. 0 plus 1, and 0 minus 1. So then 1 equals a, 2 times 1 times -1. So 1 equals -2a. Oh, so a is -1/2. Oh, that makes sense, because look at the end behavior. This is an up-down. That a would have to be negative for that to happen. You following me? I hope so, because I know I have no idea. So I'll go back to my equation. So I'm making myself laugh. Back to my equation. I'm going to change that a to -1/2. Oh boy. Oh boy. Oh boy. Guess what? We can do this. Okay? I know you're looking at me like you don't believe me, but I believe you. Find the cubic. Oh, that tells me it's cubed. Function whose graph passes through -3, 0, and 1, 2. Hold your horses, 1, 2. You are not in a 0. I'm on to you. And is tangent to the x-axis at 2, 0. Okay. So first of all, I'm going to translate tangent to the x-axis. That means that we're going to bounce on the x-axis, which that is even multiplicity. Okay. So my zeros are at -3 and 2. And 2 has a multiplicity of 2. So we'll start with y equals a. Plus 3 x minus 2. And then because of that multiplicity, the phrase tangent, say square on that. Now, that 1, 2, lovely point, but not an x-intercept. So what I'm going to do is that's going to be my other point. So what I have so far now is that bounce on 2, going through this. I need to make sure that I go through this point also. So So that kind of like that would be my sketch. Okay. So I'm going to take this 1, 2, and I'm going to make my x is 1 and my y is 2, and solve for the a. 2 equals a, 1 plus 3, minus 2, 2 equals a times 4 squared. Negative 1 squared is 1 times 4 is 4. A, and then a is 1/2. Change my a to 1/2, and that's the final answer. What I want you to do now is pause the video and try the next problem. Go ahead, you can do it. I believe in you. Alright. So, tangent to the x-axis of these two, and both to that point. So, both compounds. X plus 1 squared, x plus 2 squared, and then negative 2 equals a, x plus 1 squared, x plus 2 squared. A is negative 1/2. Right. And that concludes lesson 2.3. So to recap, we used our knowledge of factoring and behavior to create sketches like this, okay? And we're not precise for those hills and valleys, but we're precise for the general shape and where we're crossing the x-axis. We found the y-intercept where we could, which was a nice little bonus. We also wrote equations of the graphs where we had the y-axis labeled and where they weren't labeled. So where it wasn't labeled, we had infinitely many answers, and sometimes we had exactly one answer. We also did the exactly one answer once from word problems. What I'd like